Welcome to the Deep Dive, where we cut through the noise and zero in on the most crucial insights from complex topics. Our mission is to give you that shortcut to being truly well-informed, even on the bleeding edge of technology. Today, we're embarking on a fascinating deep dive into the world of multi-agent AI systems, specifically focusing on Anthropic's groundbreaking research capabilities.
Yeah, this is exciting stuff.
You've handed us some incredibly detailed source material, a comprehensive study guide, technical briefings, and our goal today is to unpack its core concepts, explore the immense benefits and surprising challenges, and truly understand the intricate engineering that makes these systems tick. Think of it as orchestrating an AI dream team.
What's truly fascinating here, I think, is how these systems are pushing the very boundaries of what AI can accomplish, especially when faced with these open-ended, unpredictable problems.
Right.
It's a rigorous, almost academic look at a cutting-edge field. We'll be exploring it step by step, just like you would in a very focused study.
Okay, let's unpack this from the ground up then. To really understand Anthropic's system, we first need to grasp the fundamental building blocks. Like understanding the individual musicians before appreciating the symphony.
Exactly. We're starting with the basics. What defines a multi-agent system, MES, in the context of large language models, or LLMs?
Okay.
It's not just one super powerful AI. Instead, it's multiple LLM agents working collaboratively. They basically break down a complex problem, distribute tasks among themselves to solve it.
So teamwork for AIs.
Pretty much. And this is a fundamental shift from single-agent systems which operate more sequentially, one step after another.
Got it. And at the very heart of Anthropic's approach lies something they call the orchestrator-worker pattern. Can you describe the distinct roles? What are the lead agent and the sub-agents doing in this setup?
Absolutely. Think of the lead agent, or orchestrator, as the project manager, or maybe the conductor of our AI orchestra.
Yeah.
It analyzes your initial query, it devises the overall strategy, and coordinates the entire research effort. Then it delegates specific, often parallelizable subtasks to the subagents or workers.
The players in the orchestra?
Exactly. They independently go out and gather information. Their interaction is quite clear. The lead agent assigns the task, and the subagents return their findings once they're done.
That collaboration sounds incredibly powerful. But my immediate thought goes to resources. Does all this multi-agent activity come at a cost? What's the relationship between the system's token usage and performance?
That raises a very important question. And yes, it does. Multi-agent systems inherently consume significantly more tokens.
Tokens being the text units the LLM processes.
Right, exactly. They use more tokens because they distribute work across multiple agents, and each agent has its own context window.
Which is like its working memory.
Precisely. It's working memory for the task. So the system scales token usage for tasks that would simply exceed a single agent's memory capacity. This enables far more parallel reasoning and, well, a more thorough exploration.
Okay.
And what's truly insightful from the sources is that token usage alone explains an astounding 80% of performance variance in browsing tasks.
80%. Wow. That's not just a technical detail. It's a profound economic insight. It means the bottleneck isn't just raw compute, but the language cost itself. Token efficiency is key.
Absolutely key.
Okay, on a different note then, another concept that stands out is the difference between dynamic versus static information retrieval. How does Anthropic's multi-step search in this multi-agent setup differ from, say, traditional retrieval augmented generation or RAG?
Good question. Traditional RAG often employs what we call static retrieval. It's largely a one-shot process. Fetch some information, generate a response.
Get docs, answer question, done.
Pretty much. Anthropic's MAS, however, uses a dynamic multi-step search. Here, the agents iteratively find relevant information. They critically adapt their approach based on what they've just discovered, and then they analyze those results to formulate a more robust answer.
So it's more like a real research process. You find something, it changes your next question.
Exactly. This iterative, adaptive capability is a key advantage for complex, unpredictable research. Like a human detective following new leads, adapting the investigation as they go.
Makes sense. Now, while these systems offer incredible benefits, they also introduce new complexities. One fascinating and maybe sometimes challenging aspect is what are called emergent behaviors. What exactly are these, and why do they pose such a hurdle?
Right. Emergent behaviors are essentially unintended or unprogrammed patterns that unexpectedly arise from the complex interactions of the individual agents.
Stuff you didn't plan for.
Exactly. They can make development and debugging incredibly difficult because you're not just looking at one agent's actions in isolation. You're looking at the often unpredictable ways agents behave together as a collective.
Can you give an example?
Sure. The sources mention that early on, two subagents might accidentally get into a loop, maybe repeatedly asking each other for the same piece of information, unaware the other is doing the same thing. That kind of redundancy is surprisingly hard to debug when it wasn't explicitly programmed.
I can see how that would be tricky. Okay, so after laying that foundation, what does all this mean for us, the users? Why are these multi-agent systems so important, especially for complex research tasks?
Well, they are particularly well-suited for addressing open-ended problems.
Hmm.
These are the problems where the exact steps or even the ultimate solution pathway are difficult to predict in advance.
Like real research often is.
Precisely. Just like human research, the process is dynamic and path-dependent. What you find influences where you go next. It requires the flexibility to pivot, explore tangential connections, maybe even autonomously delve deeper over many turns. A single agent might get stuck on a predetermined path, but a team can explore much more widely.
Okay, and here's where it gets really interesting for me. The scalability of performance. Our sources draw this compelling analogy to human collective intelligence. How does that apply to AI, and what kind of gains are we actually seeing?
It's a great analogy. The idea is that once AI intelligence reaches a certain threshold, multi-agent systems become absolutely vital for scaling performance further. They allow groups of agents to accomplish far more than any individual could.
More than the sum of their parts.
In a way, yes, and the numbers back it up.
Mhm.
Internal evaluations showed that Anthropic's MAS, using Claude.x 4 as the lead agent and Claude Sonnet 4 as its subagents, outperformed a single agent, Claude.x 4, by an astounding 90.2% on their internal research evaluations.
90.2%. That isn't just an improvement, it's a paradigm shift. It shows collective AI intelligence isn't just theory, it's a massive leap in practical capability.
It really is. It pushes the boundaries of what even the most advanced single models can achieve.
So, for what specific types of queries do they truly excel? Where does this team approach shine?
They particularly excel at breadth-first queries. These are tasks that naturally involve pursuing multiple independent directions simultaneously.
Like casting a wide net.
Exactly. For example, finding all the board members of S&P 500 IT companies. That's a task a single agent really struggled with. It's too large, too varied. But the MAS decomposed it into parallel subtasks for its individual subagents, and it successfully found the answers much more efficiently.
Okay, that makes sense for broad searches. And how do these subagents contribute to concepts like compression and separation of concerns? These seem crucial for handling massive amounts of information.
They are crucial. Subagents facilitate compression by working in parallel, each within its own focused context window. They process vast amounts of information specific to their subtask. Then, they distill the most important findings, the critical tokens for the lead agent to synthesize.
So they pre-process and summarize.
Right, which is hugely efficient.
Right.
They also provide separation of concerns because they have distinct tools, distinct prompts, and their own exploration trajectories. This reduces what's called path dependency.
Which is basically getting stuck down one rabbit hole.
Exactly. It prevents the whole system from getting stuck just because one line of inquiry didn't pan out. It enables thorough, independent investigations across multiple avenues simultaneously.
Now that we understand the what and why, the incredible potential of these AI dream teams, let's pull back the curtain and dive into the how. How is Anthropic's research system actually built? How does it execute a query from the moment you hit enter?
Okay, so it leverages that orchestrator worker pattern we talked about. When you submit a query, the lead researcher agent first thoroughly analyzes it, develops a comprehensive strategy, and this is crucial, saves this entire plan to its internal memory.
A dedicated memory.
Yes, this memory is critical to prevent truncation, even with very large context windows that might exceed 200,000 tokens. It ensures the overall plan maintains continuity and doesn't, forget its objectives during long, complex tasks.
So it's keeping its long-term strategic goals in mind, preventing it from getting lost in the weeds. Then what happens after it's formed that initial plan?
Then it creates specialized subagents. Each one gets assigned specific research tasks derived from that lead agent strategy.
Okay.
Each subagent then independently performs searches. But here's a clever part. It evaluates the tool results using something called interleaved thinking.
Interleave thinking. What's that?
It means it alternates between executing a tool like doing a web search and internally evaluating the results of that action before deciding the next step.
Ah, so it pauses to think, okay, what did I just learn? Does this change my plan?
Exactly that. Rather than just blindly collecting data, it's constantly assessing. Once a subagent completes its task and this internal evaluation, it returns its findings to the lead researcher.
So the lead researcher is continuously synthesizing those results and adapting its strategy based on what the subagents find. It's not just a one-time delegation.
Precisely. It synthesizes the incoming results, assesses the overall progress towards the goal, and decides if more research is needed. It might spawn more subagents or perhaps refine the tasks of existing ones.
And once it thinks it has enough,
Once sufficient information is gathered, a specialized citation agent steps in. Its specific job is to meticulously process all the source documents and the generated report to ensure proper attribution. It identifies the specific locations for citations before the final, well-sourced results are returned to you.
that's thorough. But this coordination sounds incredibly complex to manage. Our sources highlight that prompt engineering is really the primary lever for improvement here. Given that, what are the absolutely key principles for steering this collective intelligence effectively?
That's right, prompting is huge. A core principle is that you really have to think like your agents.
Get inside your heads.
Sort of, yeah. Understanding exactly how they interpret prompts and how they use the tools you give them is crucial. What might seem obvious to a human can be really ambiguous to an LLM agent.
Right.
Running simulations where you observe the agents working step by step immediately reveals these failure modes. It helps you develop an accurate mental model of their operational logic, how they think.
I can certainly imagine vague instructions causing utter chaos in a system like this. One agent goes left, another goes right.
They absolutely do. That's why delegation and task boundaries are vital. The lead agent needs to provide incredibly detailed task descriptions for the subagents. This includes clear objectives, the expected output format, even precise guidance on which tools to use or avoid.
So, micromanaging, almost.
In a sense, but necessary micromanaging.
Yeah.
The sources give an example. Early agents would duplicate work or miss critical information when given vague instructions like, just research the semiconductor shortage.
Right. What does that even mean?
Exactly. Some subagents would focus on the 2021 automotive chip crisis, while others duplicated efforts looking at current 2025 supply chains. Just chaos. Clear boundaries and detailed tasks solve that.
Okay, clear tasks. How do they ensure agents don't overinvest time and resources on simple, straightforward questions?
We scale effort to query complexity. This is done by embedding explicit rules directly into the prompts themselves.
Rules in the prompt.
Yeah. So a simple fact-finding task might intelligently trigger just one agent and maybe a couple of tool calls. But truly complex research could activate a rule requiring, say, more than 10 subagents with clearly divided responsibilities. These guidelines prevent wasting resources on simple queries and ensure enough power is allocated for the hard ones.
And tool design must be absolutely critical for effective delegation, too, right? If the tools are bad, the agents can't work well.
Yes, tool design and selection are critical.
Yeah.
You can think of the interfaces between agents and their tools as being just as vital as human-computer interfaces.
Interesting analogy.
Agents need explicit heuristics like rules of thumb programmed into them. First, examine all available tools, then match the tool usage precisely to their intent for that step, and prefer specialized tools for specific tasks if available. Bad tool descriptions, they can send agents down completely wrong paths. So each tool needs a distinct purpose and a crystal clear description of what it does and how to use it.
Okay, this next one is truly fascinating. Agent self-improvement. It sounds almost like science fiction. How do the Claude 4 models contribute here? Can they really improve themselves?
It is remarkable.
Yeah.
Claude 4 models, particularly the Opus version, can actually diagnose why an agent is failing at its task.
Based on its actions.
Based on its actions, its reasoning, its tool use, yes. And then it can suggest improvements to its own prompts or even its tool usage for next time.
Wow.
There's even a dedicated tool testing agent mentioned. If you give it a tool with a flawed description, it will attempt to use it, realize it's not working as expected, and then intelligently rewrite the description to be more accurate.
Seriously, it rewrites the manual.
Effectively, yes. And the sources state this led to a 40% decrease in task completion time for future agents using that newly improved description. So the system is learning from its own mistakes and becoming more efficient over time.
It's like they're training themselves. Incredible. Okay, what about the overall search strategy? Is there a particular philosophy guiding how they explore?
It mimics effective human research. Start wide, then narrow.
Ah, okay.
Agents are prompted to begin with short, broad queries. Just get a lay of the land, evaluate what initial information is available. Then, based on those findings, they progressively narrow their focus with more specific queries.
Why is that better?
It counters a natural tendency LLM agents sometimes have, which is to default to overly long, specific queries right at the start. Those often return few or no relevant results. Starting broad is usually more robust.
Got it. And what's this extended thinking mode? It sounds like a way to give them, I don't know, space to process.
That's precisely it.
Hmm.
It's a feature where Claude outputs additional tokens, kind of like a visible thinking process. It acts as a controllable scratch pad or an internal monologue that you can actually see.
So you can watch it, think.
In a way, it helps both the lead agents plan their overall approach, assessing necessary tools, decide on how many subagents are needed, and it helps the subagents evaluate tool results and refine their next queries. This visible reasoning significantly improves instruction following, complex reasoning, and overall efficiency.
Makes sense. Finally, this last principle really highlights the sheer speed gains we talked about earlier.
Right. Parallel tool calling.
Wow.
This dramatically cuts the research time. They use two key kinds of parallelization.
Okay.
First, the lead agent spins up multiple subagents, typically 3 to 5 in parallel, rather than waiting for one to finish before starting the next.
Makes sense.
And second, those subagents themselves can often use 3 or more tools in parallel for their own specific tasks, like running multiple web searches at once.
Parallelism within parallelism.
Exactly. And these changes, working together, can cut research time by up to 90% for complex queries. We're talking potentially days of work compressed into mere minutes.
Incredible efficiency gains. Okay, so building these systems is one thing, but how do you actually know if they're performing as intended? What are the unique challenges of multi-agent system evaluation? It sounds far more complex than just checking for a single right answer.
It certainly is. Traditional evaluation methods often fall short because, as we discussed, multi-agent systems are inherently non-deterministic.
Meaning they don't always do the same thing twice.
Exactly. Even with identical starting points, the agents can take completely different yet equally valid paths to reach the same goal. So you can't just check if they followed some prescribed correct steps, because we don't always know what those right steps should be for a complex, open-ended problem.
It's like judging a jazz improvisation versus a classical score.
That's a great analogy. You're judging the quality of the outcome, the creativity of the solution, not just adherence to a fixed script.
So where do you even begin to assess performance if there isn't that fixed path?
Well, the recommendation is to start with small samples first. Especially early in development, changes you make to prompts or the system's architecture can have really dramatic impacts.
So you see big changes quickly.
Often, yes. You can spot significant improvements or regressions with just a few carefully chosen test cases. Maybe a set of 20 queries that represent typical real usage patterns. A clever prompt tweak, for instance, might boost success rates from, say, 30% to 80% on that small sample, giving you quick feedback.
Okay, small samples first. But who or what judges the outputs if there's no single right path or answer sometimes?
This is where LLM as judge evaluation is proving very effective.
Using another AI to judge the first AI.
Essentially, yes.
Yeah.
Give another powerful large language model like Claude.x a clear rubric. Then it can evaluate the research outputs against criteria like factual accuracy, citation accuracy, completeness, the quality of the sources used, and even tool efficiency. This scales incredibly well. You can evaluate hundreds of outputs relatively quickly. And it's particularly powerful when the test cases do have a clearly verifiable correct answer it can check against.
But what about the things that automation might miss? The more subtle failures, maybe biases.
That's precisely where human evaluation remains absolutely essential. Humans are needed to catch those difficult edge cases. Subtle hallucinations where the AI sounds confident but is wrong, unexpected system failures, or insidious biases.
Like what kind of bias?
The sources mention an example where early agents consistently chose SEO-optimized content farms over more authoritative sources like academic PDFs, simply because the content farms were better at gaming the search results. Humans spotted that pattern.
Okay. Humans provide that unique contextual understanding.
Exactly. Insights that automated methods just cannot replicate yet.
And for systems that are constantly evolving, maybe learning over time, there's another approach to evaluation, right? Something about the end state.
Yes, exactly. For agents that mutate their internal state over many turns, meaning they change and learn as they work, end state evaluation is often preferred.
So you just look at the final result.
Pretty much. You focus purely on whether the agent achieved the correct final outcome or state, rather than trying to judge every single intermediate step it took to get there. This acknowledges that agents might find alternative, valid paths to the same goal, and ultimately the final result is what truly matters for the user.
Right, the destination, not just the journey. Okay, that makes sense for evaluation. Now, bringing these incredibly complex systems from a promising prototype to a reliable production environment, that sounds like a whole other mountain to climb. Our sources emphasize that the gap between a demo and a deployed product is often far wider than anticipated for these agentic systems.
That's absolutely right. The key reason is that agents are stateful, and errors can compound.
Stateful meaning they remember things over time.
Yes, they run for long periods, continuously maintaining context, remembering past actions and information. So, minor system failures, a tool temporarily unavailable, a network hiccup, can have catastrophic cascading effects.
Like building a complex house of cards. One slips, the whole thing tumbles.
That's a good way to put it. Anthropic mitigates this risk in several ways. They build systems that can resume from where an error occurred rather than restarting the whole task from scratch.
Checkpointing, basically.
Right. And they allow the agent to intelligently adapt to tool failures where possible, perhaps trying an alternative tool. This is combined with more deterministic safeguards like automatic retry logic and those regular checkpoints.
And how on earth do you debug something so dynamic and non-deterministic? It sounds like trying to chase a ghost through a maze.
Yeah, debugging non-deterministic agents is incredibly difficult. It requires really robust systems for full production tracing. You need high-level observability, not necessarily into every single word exchange for privacy reasons, but into the agent's decision patterns and their internal interaction structures.
Seeing the strategy, not just the tactics.
Exactly. This allows engineers to diagnose failures and find root causes by understanding why an agent made certain choices, or why a group of agents got stuck in a loop without needing to sift through mountains of raw conversation logs. It's about understanding the patterns of behavior.
Deploying updates to these constantly running stateful systems must be tricky too. You can't just stop everything.
It's a significant challenge. Deployment challenges are magnified because these agents are highly stateful and maintain long-running processes for users. You can't just pull the rug out from under them.
So how do they manage it?
They employ techniques like rainbow deployments. This involves gradually shifting a small percentage of user traffic to the new version of the agent system. They carefully monitor its performance and stability in the live environment before rolling it out more widely. It prevents a well-meaning code change from accidentally breaking thousands of ongoing agent processes.
Careful and slow. Okay. Our sources also mention a current limitation related to the system's speed, despite all the parallelization we've discussed.
Yes, that's the synchronous execution bottleneck. Currently, the lead agent often has to wait for its subagents to complete their assigned tasks before it can synthesize the results and decide on the next step.
So there are still waiting periods.
Right. This synchronous approach simplifies coordination. It's easier to manage when things happen in sequence. But it does limit the true potential for parallelism. Future goals include moving towards more asynchronous execution, where agents can work and communicate more fluidly without strict waiting periods.
But that sounds even more complex to manage.
It absolutely is. Asynchronous execution adds significant complexity in coordinating actions and maintaining state consistency across the entire system. It's a hard engineering problem.
This sounds like a truly immense undertaking, bridging that gap between cutting-edge research and reliable, real-world application.
It truly is.
Yeah.
And that jump from prototype to production is significantly wider for these agentic systems, precisely because of that compounding nature of errors we talked about. One seemingly small step failing can lead to entirely different, unpredictable trajectories down the line. It's a real testament to the meticulous engineering involved.
So, with all these complex systems and all this careful engineering, what's the actual real-world impact? How are users benefiting from Anthropic's multi-agent research system today? What does this mean for, our everyday work?
Users are reporting significant value across a surprisingly wide range of applications. We're hearing about people finding business opportunities they hadn't considered before, navigating really complex healthcare options, resolving thorny technical bugs in code.
Real practical stuff.
Very practical. And some users report saving up to days of work by having the system uncover research connections or synthesize information they wouldn't have found or put together alone. It really is a powerful knowledge accelerator.
Days of work saved. That's huge. What are some of the top common use cases for this research feature that Anthropic is seeing? Where are people using it most?
Well, the top categories currently include developing software systems that accounts for about 10% of usage. Then there's optimizing professional or technical content like reports or documentation at 8%. Business growth strategies is also around 8%. Academic research is 7%, and basic researching or verifying information about people, places, or organizations is about 5%.
Mm,
So it's incredibly versatile.
a broad range. But there are limitations too, right? Where are these systems not the best fit right now?
Yes, absolutely there are limitations. As we discussed earlier, they burn through tokens faster, significantly faster. The sources say about 15 times more tokens than a traditional chat interaction.
15 times.
Yeah. So their economic viability really hinges on the value of the task being high enough to justify that increased performance and cost. It's not for trivial questions.
Makes sense. Any other limitations?
They're also generally not a good fit for domains requiring all agents to share the exact same context simultaneously, or for tasks that involve many complex interdependencies and require real-time coordination between the agents themselves.
Like what?
Most complex coding tasks fall into this category. While they can help develop software systems, the agents aren't yet great at that kind of fluid, real-time internal delegation and collaboration needed to, say, write and debug a large, intricate piece of code together. That level of coordination is still a challenge.
Okay, that clarifies the boundaries. What an incredible deep dive this has been into Anthropic's multi-agent research systems. We've truly seen how they've systematically tackled complex, open-ended problems, how they've scaled performance dramatically with these AI dream teams, and overcome really significant engineering challenges to bring these sophisticated systems to life.
Yeah.
It's truly a testament to how intelligent agents, when working together with meticulous orchestration, can fundamentally transform problem solving.
And if we connect this to the bigger picture, I think it's clear these systems represent a really significant leap in AI capabilities.
Yeah.
They fundamentally demonstrate that collective intelligence isn't just a human trait.
Right.
It also powerfully highlights the meticulous engineering, the careful system design, and those nuanced prompt strategies that are required to build reliable, high-performing AI that can truly operate with remarkable autonomy.
For you, our curious listener, this deep dive shows that the future of AI isn't just about making single, bigger models necessarily. It's increasingly about smarter, more coordinated systems, teams of AIs working together to achieve what was previously thought impossible. It's opening up entirely new frontiers for knowledge discovery and problem solving.
Which really raises an important question, I think. As these AI systems become more capable of complex, dynamic decision-making and collaboration, what new types of problems will you envision them solving? Things that are currently beyond our reach, perhaps in your own field, your own work, or even your daily life.
Fascinating thought to leave us with. Thank you for joining us on this deep dive. We hope this exploration empowers you to think differently about the rapidly evolving future of AI.